This is Dave Tandy from AG Optical Systems, and I've been promising for a while to do a video on how we take a concept for a part to physical reality. And just wanted to show some of the software applications and technologies we use to do that. What you see on the screen in front of you is a computer-aided design application called SolidWorks. It's a very popular CAD package used extensively throughout the world to design everything from a pencil to a spacecraft. And it's a good one to have, has a great feature set, and it's used by a lot of other companies, so it makes it a little more straightforward to share files. But effectively, to design a part, you start with a two-dimensional concept, and you draw simple shapes that you can then assign dimensions to. And the part that I'm going to be showing you briefly here today, how I designed, is the backplate for one of our 14.5-inch imaging Dahl-Kirkham telescopes. And so I started out with a simple circle to define the basic shape for the backplate. And then I added these shapes right here, these rectangles, that will be used to create features that allow us to attach dovetail plates and the side truss plates. I've also added a couple small holes right here that will be through holes that we use to attach the use screws, the quarter 20 button cap screws that we use to attach the dovetail or the truss plate to the back plate. So I define this shape, but you'll notice that it's only effectively two-dimensional, the drawing is. This yellow shaded area is a projection of an extrude function where we'll actually give thickness to the part. And so once you have the drawing defined, you can then do the extrude function and add thickness. In this case, it's going to be 1 inch. So I define the areas of the drawing that I want to be extruded to that 1 inch. I do that function, and it creates now a three-dimensional object with the dimensions and the features that I outlined. And effectively, at this point, what you do now is digital sculpting, where you'll add features or subtract features. And again, you start with that same concept of drawing a two-dimensional feature. And in this case, I drew a couple holes that I want to digitally drill through this backplate, define their location and their dimensions. And then this time, instead of telling the model to extrude or add material, I tell it to cut material. And when we do that, then we have features located. And I repeat this process for all the different features that I want to add to this backplate. And there you can see there's quite a few of them over here defined in the feature tree on the left. And we just continue to go through this process, and the backplate shape starts to take place. And finally, after I've gone through this 30 or 40 different operations, I've defined all the physical features that I want present on the backplate. All the through holes for the screws, for the handles, to attach other plates to it, where we attach power connectors and the potentiometer to control the fan speed, holes for the optical path, for fans to get air, and then lightweighting pockets. And some features on the back where the collimation adjustments, the screws will go, and the springs that go in there, as well as some lightweight features back here. And SolidWorks allows you to then understand some of the other features of this. You can define a material. In our case, it'll be 6061 aluminum. And then it'll tell you how much volume the part takes up, what it weighs. And you basically repeat this process for all the different parts that go in the telescope. And once you're done doing that, you can then assemble all of them virtually, of course, by using different features where you align holes, align surfaces. You can add different colors, obviously, different types of visual patterns to simulate what a part's going to be made from. You can see there is an Optec Gemini rotating focuser CAD model Once we have this, then we can determine the overall dimensions, the overall mass of the telescope, its center of gravity, and use it for a lot of good purposes. For example, we recently built an observatory, and so we had models of the paramount mounts that we were going to use in the observatory, models of the telescopes we're going to use in the observatory. So we're able to build a virtual observatory and move the telescopes around just to make sure we have the clearance that we'd like. So once you've gone through this process and defined all these parts, you're about a third of the way there. The next step is to take one of these parts and import the CAD model into a CAM software, computer-aided machining. And this bit of software will take one of these parts, it'll analyze features on it, and then you can assign all different types of tools to machine it. And I'll open up that software here in just a second and show you how we then generate all the code that goes into our CNC machines that'll then actually physically machine the part. Okay, so what I've done now is opened up our CAM software, and we use a couple different applications here. Our most recent one that we purchased and use for some other business activities is called Gibbs CAM. And rather than showing you how I program a moderately complex part like the backplate, here's a real simple part that we machined. And what we do is we import the CAD model into Gibbs CAM, and then we go through a process of defining various features, such as holes, outer machining operations, and there's really kind of the sky's the limit sort of things you can do, from just simple holes to complex three-dimensional tool paths. And it's a little bit involved, but again, it's just kind of a step-by-step process that we use. And you can see over here, we have a couple different tool paths that we've defined. And what this shows is how the tool that's going to machine this pocket, how it's going to come down, basically do a ramp, a helix type of ramp into the part until it hits the appropriate depth. And then it's going to follow these tool paths to machine out this part. And there are a lot of different types of tools that you can use to do this, different sizes. But the general class of tool that you use to do this is called an end mill. And we've defined a category, basically a library, I should say, of a lot of different tools that we use. And so what I will do is I will select the feature that I want to machine. You can see it's defined here by this royal blue line. Then I'll choose a tool and bring it down here. And I'll open up a dialog. There's different types of tool paths that you can use. Some are more efficient than others. And so in this case, I have selected a tool, and it's tool number 8, which is that end mill. You can see it's a 3/8 inch carbide finishing end mill. And once I've selected that tool and selected what's called the volume mill tool path, I'll then go in and enter parameters. What RPM I want the tool to run at, what feed rate, and that's in inches per minute, and the cut width. So the end mill will be moving at around 200 inches per minute, and each time it steps over to do a new cut, it's going to move about 60 thousandths of an inch. And so what it does is it does this process. The software is smart enough to understand how it needs to move that tool to clear out this area. And oftentimes some of the radius, some of the curves will be sharper than the tool that you're using. So you'll have to come back and clean up the pocket to make sure you remove all the material. And it's easy to sometimes overlook that a little bit. So here is what's called a contour toolpath. And you can see it basically follows the shape, and it does a finishing operation. Because when you're driving the end mill very fast at a high speed, oftentimes it leaves the wall can be a little bit, have some texture on it, maybe a little bit of chatter, depending on how hard you're driving the tool. And so you'll leave maybe 20 thousandths thickness material on the wall and come back and do a nice, smooth, slow finish pass, so you can have a very high quality finish on there. And the feeds that you use and the speeds and the RPM, a lot of these CAM packages, we'll make recommendations, but a lot of it comes down to just experience, how many times you ran this part, how well you know the end mill type you're using cuts through aluminum or steel or what type of material you're machining, and also how hard you want to push your machine. If you're a production shop trying to do tens of thousands of these things a year, you'd push your tools really hard because volume's important. In our case, we're not a production shop doing a ton of parts, so we're more interested in having speed and efficiency, but also making sure that we maximize our tool life. So once we've defined these tool paths and the direction they're going to run, how fast they're going to run, what types of cuts and patterns they're going to follow, we're able to run a simulation. And the simulation is very useful because on more complex parts where you have a lot of operations, it's easy to overlook something. And you hate to find out that you've made a mistake when you go out onto your CNC machine and you're actually running a metal part, because bad things can happen. So this allows us to run a simulation to show how the tool is going to actually machine the part. We'll speed it up just a little bit. And you can see it does a helix type ramp down the part, and now it's doing that volume mill tool path. And what this software will tell us, it gives us an idea just to visualize how the cutting should occur. And also, if the end mill is going to slam into the part, the software is smart enough to give you a warning to let you know that it's going to gouge it. You could break a tool, things along those lines. And so once we're satisfied with our tool path, then what we'll do is tell the software rather, to generate what's called G code. And G code is the code that we then feed into the CNC machine, and it contains all of the tool paths, the feeds and speeds, everything that CNC machine needs to know in order to properly machine this part, to include coordinate systems, dimensions, are you moving an absolute or incremental type of steps and things along those lines. And every CNC machine has, from different manufacturers, has what you could say is a slightly different dialect. Down in Alabama, we speak a little differently than up in New York or up in Canada. And CNC machines from different manufacturers are the same way. They have slightly different types of G code that the machines prefer. So basically, we have a couple different machines that we use, and we'll select what machine we're going to machine the part on and then generate G code. And this is an example of G code for that 14.5-inch IDK part. And you can see basically it's a bunch of different types of code that set parameters in the machine. And then it contains X, Y, and Z coordinates that tell that end mill how to move through the part, along with what type of RPM. M8 turns on cutting coolant, which helps keep the materials cool, helps prevent buildup on the end mill, and also washes away chips. And the CNC machine will then process through all of these changing tools to machine that part. And what we'll do now is show you some video from one of our CNC machines actually machining a part. So here's one of our Akuma CNC machines executing a program that we loaded into it to machine, in this case, a composite mold cavity. The spindle is turning at about 15,000 RPM, and the cutting tool is moving at about 300 inches per minute. And this is how we machine parts in aluminum.